All right. So now that we have discussed about ANOVA and the alternative test you use if the assumptions of ANOVA have not been met, we want to talk about a situation where you are dealing with variables that are actually not continuous, but say binary or ordinal or nominal. If the outcome variable is binary and you want to determine the difference between or amongst proportion, you use the chi-square. So let me just show you variables that we are looking at in this case. Sex and nephrotoxicity, maybe even treatment. So these three variables here, as you can see, sex, there is male and female. Nephrotoxicity, there is yes and no. And treatment, there is, you see already from the way it has been aligned, AZT is running from number 1 to 67, then followed by TDF. It's already showing that I just made this variable up. TDF, and then there is D4T. See? Such variables can actually determine whether there is a difference in the proportions by using the chi-square. The outcome variable has to be binary. So you can actually determine by drawing up a table. So you can say tabulate, for example, you can say tabulate sex, and it will tell you that you have 120 females, which is 59%, or 0.59 as a proportion, and you had 83 males, which is 40%, or 0.41% of males. You get the sense? These are the proportions. You can also tabulate nephrotoxicity by sex, where you want to say, you want to see how many of the people of different sex had nephrotoxicity. So you just say tabulate nephrotoxicity sex. As usual, you see the outcome variable will be written in these rows, while the exposure variable will be written in the columns. So when you look at this table is referred to as a contingency table. And what this contingency table is telling you is this, that amongst the females, there were 89 females who had no nephrotoxicity, while 31 females who had nephrotoxicity, the outcome nephrotoxicity. The total number of females was 120. Amongst the males, we had 69 males who had no nephrotoxicity and 14 males who had nephrotoxicity, giving us a total of 83 males, which we know they were 83. In the same vein, we had a total number of 83 females without nephrotoxicity and 69 females without nephrotoxicity, giving us a total of 158 persons without nephrotoxicity, while we had 31 females with nephrotoxicity and 14 males with nephrotoxicity, giving us a total of 45 persons who had nephrotoxicity. Summing everything up is going to give you total of 203 persons, which gives us the total sample size. This is a contingency table. Okay? It can actually even show as the percentages. Sex, say row, it's giving us the percents. So it's telling us that we had 89 females, which is 56% of the females had non-nephrotoxicity, and 31, which is 68%, had nephrotoxicity. Okay? Then, same thing here. This is actually going in the row, ideally. So, this is the females were 68% compared to the males who are at 81%. So, it's going in the row. Okay? So, you can say this, it gives us a total of 158. So, you're saying you had 89 females, so it's 89 over 158 is 56%. And 69 females out of 158, which is 43%. Okay? Again, we had 31 out of 45, which is 68% of the persons who had nephrotoxicity, and 14 out of 45, which is 31% of persons who had nephrotoxicity. So when you put the command row, it's actually checking amongst those with the outcome. If you put the command column here, it's going to do it amongst those with exposure. So those that were exposed to nephrotoxicity by sex, right? So it's going to tell you that we had 89, which is 74% of the females, which is 89 out of 120, 74% of the females non-nephrotoxicity, and 31, which is 25% of the females had nephrotoxicity. This is in the columns. So you're going downwards. So you put the command columns, it's actually making the percentage using the column. When you put row, it will make the percent using the row or the outcome variable. So now that we have this, you are actually able to determine whether there is an association between the sex of the patient and the risk of nephrotoxicity. Okay? Is there an association between the sex and the risk of nephrotoxicity? So how you do it is the same command, tab, nephrotoxicity by sex, chi2. So it's just saying chi-square. Do a chi-square test to determine whether there's an association between nephrotoxicity, which is the outcome, and sex. And it's telling you that there was no association between sex and nephrotoxicity because the p-value is actually greater than 0.05. Is that clear? Is that clear? What's the null hypothesis of a chi-square? There is no association. So this is just telling you reject the null hypothesis. So to reject the null hypothesis that there is no association, since the p-value is greater than 0.05. Right? So to reject the null hypothesis, as the evidence against the null hypothesis is very weak. You see what I mean? You fail to reject the null hypothesis here, that there is no association. Remember, you reject the null hypothesis if the p-value is less than 0.05. So here you fail to reject the null hypothesis that there is no association. The null hypothesis is that there is no association between the males and the females. So fail to reject that null hypothesis to mean there is no association between the males, between the sex and nephrotoxicity. You get the sense? Now, this chi-square test can be used only if the assumptions of the chi-square have been met. Some of the assumptions of the chi-square include that the sampling of the participants was done randomly and independently. It is also that the variable observes a chi-square distribution. Also, that 80% of the observations in each of these squares of the contingency table should be above 5, which means if you look at this, it just means all of the observations here must be above 5. Because since there are 4 squares, if it's 80%, it means like more than 3, right? Should have 5. So now, here, if for example we had a 5 or a 4, then it means the assumption of the chi-square has failed. You can't use the chi-square. In fact, other books actually use 8, not 5. So just to be sure, you might want to be more reserved when you're using the chi-square and avoid using it if any of the squares has an observation less than 8. Because other books recommend 8. Okay, so if there was an 8 here, then you can't use the chi-square. Okay, there was a 7 in any of these squares. If there was an observation, not a 14 here, but there is a 7, for example, it means the assumption of the chi-square will have been violated because the sample size is small. Because the chi-square should actually assume that the sample size is actually large enough, and each of the squares would have observations more than 4, more than 8. Let's say 8. So if this or this or this, any one of this is less than 8, just know there is a violation of the chi-square. Other books use 5, but to be more reserved, use 8. Okay? Now, what would you do in that case? If the assumptions of the chi-square have been violated, you can't use the chi-square. You use the alternative of the chi-square, which is the Fisher's exact test. Guys, these statistical tests, the parametric and the non-parametric alternative of them, you just have to basically master and know them. So, how do you do this? You say, tabulate nephrotoxicity by sex. Okay. That. By sex, chi2 exact. We write away the exact. So it's going to give you here the Fisher's exact test. So this is Pearson's chi-square. The p-value is 0.13. The Fisher's exact test. You don't use the one-sided Fisher's, you use the two-sided. The Fisher's exact test is showing a p-value of 0.169. It's also telling you that there is no association between sex and the risk of nephrotoxicity. Yeah. Yes. When you say one-sided, maybe the easiest way of explaining this is that you have already taken a side and said the males are at higher risk than the females. The two-sided is that, so in this case, you would actually say there is an association between being male and having nephrotoxicity. taking one side. While here, the two-sided would be there is no association between sex, or either sex, and toxicity. Yeah. So if it's in a continuous variable, you would actually say the females are at higher risk, would have higher EGFR than the males, for example. You're already taking the one side here. And that is not desirable in research. Okay, so this is what you use as the alternative test for the chi-square, which is Fisher's exact test. I must show you. I actually gave you an assignment. I think in some of those questions, you would notice that there is a question to say, determine what the degrees of freedom were. I think you need to go and check this. How do you determine the degrees of freedom that you have in a chi-square using the number of rows and columns that you have? You have to go and search that. There's a question in that. And also, you should be able to compute the chi-square manually, so that you understand. So I want you to go and learn how to compute the chi-square manually because it's obtained from these values. And then I want you to also go ahead and learn how to determine the degrees of freedom. Because you might be asked a question, such as the questions that are there in your test, they are actually just giving you an explanation. Say, this number of participants were enrolled in the study, this many had nephrotoxicity, this one, and things like that. Then ask you today, draw a contingency table. When you're asked to draw a contingency table, you're asked to draw this. Is that clear? Then you even put in the percents, the chi-square is able to be computed. Is that okay? Chi-square computed manually, you should be able to do that. The next thing is that you can actually use a chi-square even when you have more than two groups. So when you say tabulate nephrotoxicity by treatment, for instance, when you know that treatment has more than, so let's see, column, treatment has more than two groups, you would get a table such as this, which is saying that the treatment variable being the exposure among a patient exposed to either of these three treatments, and then the outcome variable here is nephrotoxicity. Take a note that when you're doing statistical tests, the outcome variable is written first, and then the exposure variables are written afterwards. So this is simply telling you that those that took AZT, you had 50 with no nephrotoxicity, which is 74% of those that took AZT, and then you had 17 out of 64 who had nephrotoxicity, which is 25%. In the same vein, you had 55 out of 68 who had no nephrotoxicity, which is 80%, and 13 out of 68 who had nephrotoxicity, which is about 19%. Again, you had 53 out of 68, which is 77% of those who had no nephrotoxicity in D14, and you had 15 out of 68, which is basically 22% with nephrotoxicity rather. So you can still even do a chi-square, since it tabulates nephrotoxicity by treatment, use chi-square. And here again, it's telling you that there is no association between treatment and having nephrotoxicity. There is no association between treatment and having nephrotoxicity. Is that okay? So this was just to show you that a chi-square can even be used if you have a nominal variable, such as treatment with TDF. Treatment, different kinds of treatment. This is 1, 2, 3 possible categories. You can still use the chi-square as long as your outcome variable here is binary. Is that clear? So, I think this is where we're going to end today. Any questions before we bring this to a close? Are we okay? Should I take it that